And that, unfortunately, allows the soil to relax inwards slightly. We might, in various pile techniques, try and support the sides of that hole so we can reduce the amount of relaxation, but it's very hard to prevent all relaxation. So there's two things about board piles. One, the hole we create is rough, and there I've drawn it on a scale, but it's rough on a macroscopic level, to the point where when we get failure, so if I draw on this diagram here, so let's just make it a pile looking like so. This diagram won't work. Yeah. I need to redraw my pile to make the diagram work. So if we have a pile which is rough like so, and I made very stubby, the failure surface we get when we fail that pile, if we push it into the ground, tends to not follow the surface of the pile even. It tends to cut down like so. It will just shortcut between what we call the asperities, the lumps. So when the pile fails, the failure surface may not even be right on the surface of the pile, or at least it won't be continuously on the surface of the pile. So the two features from board piles which we see from the method of assertion are the hole into which the pile is cast is quite rough on a macroscopic level, but the soil around the hole has been allowed to relax towards the hole during pile construction. So these processes will again affect the pile design parameters. That's why we need to know about types of pile. And I should say at this point, I have chosen two generic types of pile, representing the two extreme camps. There are proprietary ways of inserting piles which act as a sort of combination of the two. So there are probably 20 or more ways of putting piles into the ground, but in character they either verge towards the driven pile type scenario or they are towards the board pile. So I'm not trying to say these are the only two types of pile. I'm trying to say these are two categories of pile, and the processes, the thought processes about the design parameters we're going to use are the same thought processes you have to use when using these proprietary types of pile. And by which I mean, if we go back to this picture, that's a continuous stem auger, but you can get hollow stem augers. So there's a pipe down the middle of the auger. So for one type of pile is to bore all the way down to the bottom, but instead of leaving it completely unsupported, you inject the concrete from the bottom of the hole and gradually bring the auger to the surface, leaving the concrete behind. And for that type of pile, you get slightly less relaxation than you would with a completely board pile. So there are little tricks they use in construction, usually developed to cope with particular soil types, particular geological situations. Okay, so that's why we need to know about method of insertion. What about pile function? Well, the reason we have to know about descriptions based on pile function is because we always have to remind ourselves that in civil engineering, we work as part of the team. And you must communicate your design decisions to the construction team. It's quite unlikely, if you do the design, that you'll be out on site during construction. It happens once in a while because people get redeployed, but it's quite unusual. So we'll talk about pile function. So with the light from the window, it's hard to see. There's supposed to be a firm strata. So the first type of pile is called an end-bearing pile. This is the classic type of pile where you believe you have, for example, soft alluvial clays overlying either a dense gravel layer or possibly over-consolidated glacial clays, or possibly, if you're very lucky, bedrock. And what you do is you pile down so that your building rests on the firm layer. Very little stress is transferred to the weak soil. If you're going to build this type of pile, why do you need to communicate that decision? Well, if you're boring a pile, you saw the picture of the boring. You saw these great clods of soil being thrown all over the place. And after boring, it's common to have quite a few of those sitting at the bottom of the hole. If you build a pile and you've got clods of soil at the bottom of the hole, then the first thing that will happen when you put a building on it is those clods of soil will compress and you'll get an increment of settlement not associated with the foundation, but merely associated with poor construction technique. So one of the things you need to do when you're looking at bored end-bearing piles is make sure, they call it mucking out, you have to clean the bottom of the hole thoroughly. What about another type? Here, we're supposed to have a deep deposit of clay. You've got no firm layer to end bare on, but by putting a pile into the ground, you transfer the load. Rather than being transferred to a little zone at the surface, you're now transferring the load to a large volume of soil. So the same load will result in lower stresses by being transferred to a larger volume of soil. A friction pile develops most of its capacity by shear stresses on the side of the pile, which is why it's called a friction pile. There is an end-bearing stress, but it's not usually the major component of capacity. I should add over here, you do get shear stresses on the side of the pile in the weak soil here. What we're saying is that the shear stresses on the side of the pile are generally tiny compared with the end-bearing pressure there. And so we are characterising behaviour. Why is this important? Well, one of the things you can do, imagine trying to bore an open hole in a very soft, loose material. We've said the soil likes to relax inwards. Well, in a really weak material, it might start collapsing into the hole. One of the techniques we can use to support that hole during construction is to fill the hole with a drilling mud, a bentonite slurry. These muds have a high density, not quite as high as the soil itself, but higher than water, and they are thixotropic. So when they're left in undisturbed, they have shear strength. But as soon as you put the auger through them, they lose their shear strength. So you can drill through a drilling mud and support the hole with the drilling mud pressure. The only thing about that is it tends to leave a coating of the drilling mud around the shaft of the hole. And the friction of the drilling mud is lower than the soil usually. So if you're out on site and you've got some bored piles and the construction team are having trouble with supporting the hole during construction, you don't want them just choosing to use drilling mud without first speaking to the design team, because if you reduce the friction on the shaft of the pile, you reduce the capacity. So it's about communicating the idea that, in this case, the end bearing is the important mode of pile support. In this case, it's shaft friction. So the construction team makes sensible decisions when trying to get the piles into the ground. And it's a feature of construction that the job isn't easy. You have to make a lot of decisions on site as you go in order to make it buildable. And what you want as a designer is for those decisions to be compatible with your design. The third common type of pile is what we're calling a laterally loaded pile. This is the sort of pile you may use for a bridge abutment. So on top of here, you've got a wall and a bridge, and there's soil behind that retaining wall. We've all seen this sort of detail, haven't we? So I'll find another sheet of paper. Sort of situation I'm talking about now is there's perhaps your river channel. there's your soft alluvial soil, and what you're going to do, and maybe this is the gouge channel in the firm strata from the... And what we're going to do is build some sort of retaining wall there. So we can put a bridge across the river, and behind there you have soil, so the vehicles can approach on an embankment, go across the bridge like so. And if this was a soft soil, and this is stiff, a common solution is to put piles through like so. If it's a stiff soil, you actually key them into the stiff soil. If it were rock, you might just end bare on the rock. So that's the sort of foundation you end up with. And, of course, the embankment there has a horizontal pressure on the abutment wall there. So what you get are laterally loaded piles, like so. Piles are reasonable. I mean, if your lateral loading on your piles is less than 10% of your axial capacity, you can normally ignore it. So here we're talking about more substantial loads, so they only tend to arise with things like bridge abutments. OK, so I've talked about those. I wanted to go back to here. The other categories of piles you get tension piles. Tension piles are really useful for things like electrical power transmission towers. So you get what are very open gantry type structures, so they are relatively light compared with the wind loading they attract because they're tall, often crossing hillsides. And so if there's wind loading on a tall tower, you can get tension in some of your foundations. And piles, because they have this friction capacity, can resist tension. So a tension pile, the notable thing about it is it has no end-bearing capacity, it's merely a friction pile. Settlement-reducing piles are a rather special category. Sometimes, underneath a raft, we'll put piles in which aren't necessary from bearing capacity, but they reduce the settlement of the raft. So I'll leave those to one side because they're somewhat specialist. Where have we got to? Yeah, we've been through that to there. OK. That brings us to now we understand how piles have got into the ground. We're now starting to understand some of the consequences of putting them into the ground. We're ready to start looking at how piles resist load. And what I have here is I'm trying to look at the shaft of a pile. So here's a pile, and in my mind's eye, I put a cross-section through the pile and the soil, and I've drawn little lines, a grid, onto the soil. So it's very much a schematic picture to illustrate what's going on. When we apply load to a pile, what tends to happen is, obviously, the pile displaces downwards, and it causes the soil around the pile also to deform downwards. When we look, and remember, this is a cross-section. So this here, if we look at it on this diagram here, is a concentric cylinder. So we've got a cylinder of soil running round, and this is the other half of it. So we're not seeing in two dimensions, we're seeing it as part of a cylinder of soil. And what we find is the cylinders close to the pile deform a lot, and as you move further away, the deformation decreases. And there's a good reason for that. Next thing that is observed is the way the load's transferred to the soil is there's very little change in